Well, good morning, everyone, or whenever you happen to be viewing this, or wherever you are in the world. Mike D, our guest today, is broadcasting from Groningen, which I guess it's 5 or 6 in the evening there. And today, Mike is going to be talking about his projects and his work and sort of the work collectively of a lot of people over the years, but that Mike has been pushing quite recently on trying to improve chronologies by taking advantage of basically spikes in radiocarbon production in the atmosphere due mainly to solar events, but potentially to other cosmic events. And really trying to get things down to, if I would put it, like human timescales. Calibration can really, leave us with relatively imprecise chronologies at some points, but through different techniques, we can try to bring things down to human lifetime scales, events, 20, 30 years or less, that type of thing. Really a long time goal of radiocarbon, potentially now within reach. As I said, Mike is at the University of Groningen, trying to pronounce that correctly, or ish. He's an assistant professor of isotope chronology. He got his PhD from Oxford in 2009 and worked there in the accelerator unit and as a postdoc, and then also as a Leverhulme Trust Fellow from 2013 to 16. After that, went on to Groningen. He was awarded a European Research Council starter grant of £1.5 million, I believe, or euros, whatever. A lot of money for what's called the ECHOES project, which is an acronym for Exact Chronology of Early Societies. And I'm very pleased to have Mike here with us today, and I will pass it off to him. As always, we have the Q&A box. Typically, we'll try to answer the questions at the end of Mike's session. If there's something pressing, we might be able to jump in and ask him directly at that point. But go ahead and start. If you have questions, please pile them up there, and I'll moderate that at the end. So without further ado, I'll pass it on to Mike.
Well, thanks very much, Brendan, and thanks very much for an excellent introduction that really did cover everything I'm going to talk about, and in fact the reasons for doing this sort of research. Indeed, the ultimate objective of my work at the moment is to try to establish an exact year method of radiocarbon dating. So what I'm going to do is talk a little bit about the fundamentals of radiocarbon again, to recap that for those who are not familiar, and then go into where we were perhaps in about the 80s, when you had simple calibration against usually a tree ring chronology, and you were able to get precisions at best down to about a century. Soon after that, there was the advent of Bayesian modeling in radiocarbon dating that I also spent a lot of time on, in sort of the noughties, that sort of time period. And that reduced precisions down to the decade in certain circumstances. And I'll go through some of those. And then I'll spend quite a bit of time talking about our project and how its ultimate goal is to try to date things using radiocarbon measurements to the exact year. So the story of radiocarbon begins in deep space, really. In the galaxy, due to what we think are probably supernova and lots of other highly energetic processes, lots of particles are flying around all the time, ejected from these major events. Some of them, all the time actually, end up striking the Earth, and coming in and hitting the Earth's atmosphere and splitting up atoms, splitting up nuclei in the upper levels of the atmosphere. And this process releases a lot of neutrons, breaking up oxygen and nitrogen nuclei and things like that. And that frees up a lot of neutrons in the upper atmosphere. These are soon after captured by nitrogen, and radiocarbon is formed. If we weren't constantly bombarded from space by what are called cosmic rays, even though they are actually particles. Originally, people thought they were, like light, electromagnetic radiation, but actually they're particles. If we weren't constantly being bombarded by these particles from all the activity in the near Earth and in the galactic environment, radiocarbon would have disappeared off the Earth many years ago. Due to radioactive decay, but it is constantly being formed in the upper atmosphere. From there, it is oxidized to carbon dioxide, and the carbon dioxide is fairly evenly then distributed around the Earth's atmosphere, around the hemispheres. There's a slight difference between the southern hemisphere and the northern hemisphere, just due to the non-mixing of the air masses, really. But by and large, it's relatively equally distributed around the Earth. And it's indistinguishable at that point from carbon dioxide that contains carbon-13 or carbon-12. And a lot of it is taken up into plants via photosynthesis. Plants that absorb carbon dioxide in order to make glucose and make their structures. A lot of plant material is cellulose that directly comes from the absorption of carbon dioxide from the atmosphere. So at that point, it basically enters the biosphere and is locked up in chemical compounds. That process goes on as organisms are living, as they are constantly ingesting carbon from the environment. Plants photosynthesize carbon dioxide, animals eat plants, or they eat other animals. So one can think of the radiocarbon concentration in living tissue, even all the way at the top of the food chain, like humans, as being approximately the same as the concentration of radiocarbon in the atmosphere at the time that they're alive. When they die, when trees and plants are cut down or die, burnt down, when animals die, this process of building in tissue, regenerating tissue, ceases. Indeed, your own body is actually not made up of many molecules that survive from when you were first born. If you think of your hair or your fingernails or whatever, it's much of your body tissue is turning over all the time with the food you're eating. And nobody eats food that's hundreds of years old, right? You eat fresh food. So you constantly replenish this concentration of radiocarbon in your body. Even in your bones turn over as well. But this process obviously stops when you die. And so thereafter, the radiocarbon concentration in those bones is going to decline. And this is the famous exponential decay and indeed the half-life of radiocarbon, where half the material is gone and then half the material is gone again in the same amount of time. That half-life in radiocarbon terms is about 5,500 years. Indeed, when it gets so low, back 10 or 11 half-lives around 50,000 years ago, there's so little remaining in any tissue that we can't measure it. But until that point, the process of radiocarbon dating seemed like it would be quite straightforward. You have a living tissue ingesting a lot of radiocarbon from its environment and mixing that in amongst its own stable carbon forms, carbon-12 and carbon-13, the stable isotopes. This is, of course, grossly overscaled, not just the size of the isotopes, but the proportion of radiocarbon, which is infinitesimally small compared with the amount of carbon-13 and carbon-14. However, a growing organism takes in radiocarbon whilst it's alive. And then when it dies, that radiocarbon will slowly decay over time in accordance with the radiocarbon half-life. So in the beginning, it seemed like quite a simple procedure, radiocarbon dating. What we thought we would do is just measure the radiocarbon concentration in the tissue of that material, and we could then extrapolate back to when the original organism was alive, when it stopped ingesting fresh radiocarbon from its environment. We do that with an accelerator mass spectrometer. Essentially, the 3 isotopes of carbon, usually in the form of graphite, though some laboratories have the ability to measure carbon dioxide gas directly, but usually in the form of graphite, the carbon is ionized, and all 3 ions are accelerated through the mass spectrometer at high speeds, striking magnets and electrostatic analyzers and so on over this side, over the high energy side, and split. Indeed, what happens is they're originally ionized as anions, as negative ions, and in here, at the very high point of the potential, this is our accelerator, actually it's 180 kilovolts, the ions, any molecular ions that are flying through are broken up. So you might have CH or CH2 still flying through here, but it goes through a gas barrier here, a helium gas barrier that rips off electrons and so on and breaks up all the molecules. And on this side, actually, you have positive carbon ions. But the point is that these positive carbon ions are fired out at very great speeds over here. They hit these magnets and they're split into 3 beams in accordance with essentially their mass to charge ratio. So essentially by their mass. And that way, the ratio of radiocarbon in the sample can be measured right at the end. The ratio of, say, carbon-12 to carbon-14. And that was really how we thought we would get the dates for radiocarbon analysis. We just measure how much radiocarbon was left in that sample, and we had to work out how long it had been since that organism was alive. That all seemed rather simple, but then we discovered in, I guess, earlier than this really, but calibration began in sort of the 70s and 80s, that the atmospheric concentration that was being absorbed at the beginning of the food chain at the time of photosynthesis by the plants was not always the same. Indeed, the American man who invented this method, Willard Libby, knew that it was an assumption that the radiocarbon concentration in the atmosphere was constant. He figured that that might not be true, and it turned out it wasn't true. The atmospheric concentration of radiocarbon in the environment was always changing back through time. So that relationship between the living tissue amount and the atmosphere that we take to be about the starting point of the radiocarbon clock, now every year there was kind of a different starting level. So it wasn't possible to just make a measurement and then multiply it by the half-life and work out how long it had been since that organism was alive. The only way now to do radiocarbon dating was to calibrate the dates. And I'll come on to what that really means just now. So what is causing all these variations of radiocarbon in the atmosphere? If we're being bombarded from space by particles all the time from all these galactic and even intergalactic activity, all these particles flying in from many millions of miles away, surely that would average out over a year, and you would have approximately the same amount of radiocarbon produced in the atmosphere every year. Well, it turns out that it's greatly affected by the activity of the sun. If the sun is very energetic at the height of the 11-year solar cycle, and the solar wind is very strong, and all this plasma streaming off the sun, all these charged particles that envelop the Earth, if that's very active and very powerful, the geomagnetic field lines around the Earth close in, much like, like a stone in a river, and the current becomes stronger and the geomagnetic field lines close in around the Earth, and actually we get better protected from the high energetic particles that tend to come from further in the galaxy. The sun does not really tend to eject particles at the energies sufficient to break up nuclei in the upper atmosphere and create radiocarbon. Most of those particles come from much further out in space. But when our field lines are closed over like this, then we're much more protected. So actually, you can see the 11-year cycle. If you measure radiocarbon very carefully in the atmosphere, you can see it fluctuating with the 11-year solar cycle. So this modulation of the production of radiocarbon by the sun is one of the reasons why it changes from year to year. More particularly, and probably more extremely, the radiocarbon concentration changes due to really the action of the oceans, the climate generally. As you would have seen earlier, quite a lot of the radiocarbon goes straight into the ocean as well. Actually, the vast majority of it does after it's produced. But if the Earth is frozen solid and there's a lot of ice everywhere, actually a lot more is retained by the atmosphere. So the concentration in the atmosphere is enriched actually during the ice ages. So we can see those sorts of climatic events back through time in the radiocarbon record too. And the activity of the oceans and upwelling and churning and stirring of the oceans is a big component in the carbon cycle, and indeed in the radiocarbon cycle. More recently, fossil fuel burning has, of course, thrown up a lot of carbon dioxide into the atmosphere that is deficient in radiocarbon. That's because it comes from things like oil and coal, which are very rich in carbon, but they've been buried under the earth for millions of years. So any radiocarbon that was in there is all degraded away, all radioactively decayed away. So the isotopes produced by fossil fuel burning are all carbon-12 and carbon-13. So they tend to dilute the concentration of radiocarbon in the atmosphere. Additionally, there are all sorts of other Earth processes that could affect the concentration of radiocarbon in the atmosphere, such as volcanism and the like. Oopsie. So we had to devise a way of producing reliable dates now that we had a changing starting concentration of radiocarbon in the atmosphere. And this involved what I'm going to call simple calibration. And the way to do it was this: we had to have really a record of what the starting concentration was in the atmosphere of radiocarbon back through time. And to do this, we went to natural archives, and in particular tree rings. So you'll probably know that you can, from when you're a young person, you know that counting the rings of a tree gives you an idea of the age of that tree. Well, actually, tree rings are an extraordinary paleo resource, really, by taking long-lived trees with many rings, and also by dredging up fossil wood from swamps and so on, and by matching their ring width patterns, like matching barcodes, we have been able to put together dendrochronological archives, tree ring archives, that stretch back as far as 14,000 years in some cases, within which you know exactly which year each of those tree rings was laid down. So you can go to the year 5226 BC and take out a tree ring that grew in that year. So by knowing that the decay rate of radiocarbon hasn't changed in that time, we can work back from then to now and work out whether in that year radiocarbon was higher or lower than what we're going to take to be a sort of standard atmospheric activity. And that way we were able to define a new record, a record going back through time that adjusts for the concentration of radiocarbon in the atmosphere. Before 14,000 years ago, the tree ring record, the conjoint record, breaks down. There are trees much older than this, but we can't connect them to the later archives. So we go to other, perhaps slightly less reliable resources, but still very important. Things like lake sediments and forams. You get varved foraminifera, which are essentially plankton in the ocean. And you get the ones that grow on the surface of the ocean, getting a relatively a close to atmospheric concentration of radiocarbon. And when they die and fall to the bottom, they form these layers in some particular parts of the ocean. They form these layers, and you have varves of forams. And of course, because their shells contain carbonate, you can measure the radiocarbon in them. So in each case, you have these varves, which means annual layers of carbon-containing materials, just like tree rings, really. Perhaps not quite so reliable as tree rings, but they stretch back all the way to the limit of the radiocarbon dating method, beyond 50,000 years. So the process of simple calibration goes a little bit like this. We make a radiocarbon to carbon-12 estimate by using our accelerators generally now. And then we calculate what we call now a sort of conventional radiocarbon age, or a radiocarbon determination is probably a better way of putting it, because it's not really a date, it's just a measurement based on the isotopic concentration of that sample. And then what we have to do is compare that value against this blue line, which comes, in this case, from the tree rings. And it has little undulations and fluctuations in it, and they reflect the changing concentration of radiocarbon in the atmosphere going back through time. The information that we've been able to get from the tree ring records and so on, how it's sometimes been a little bit higher, sometimes been a little bit lower than a standard value. So essentially what we do is we compare our measurement with the atmospheric record from the tree rings, and of course we know the age of those tree rings, so that's essentially how we get the date, by projecting it down there onto the horizontal axis. As the original measurement is effectively Gaussian, you have a higher probability in the middle of that measurement of getting a date in this sort of range, in here. So this is actually, this gray distribution is actually a probability density function, which tells you approximately how probable each of these years on the horizontal scale actually is. As you can see, there's a little gap here where it's not really so probable, and here it's very probable. And that gap actually comes because you see the red, the height of the red measurement here deviates a little bit from the calibration curve here. So it's not very probable it's here, but it is a bit probable it's here, and most likely that it lies in this range. But we tend to summarize, because it's a very irregular, they're very irregular and hard to really express averages for or anything, these probability density functions. We tend to summarize them with highest probability density ranges. So this is the 1 sigma range here. It actually has 2 parts to it. The 68% range expressed up here, and then underneath that is the 95% probability range. And that's the one we tend to stick to in radiocarbon. Indeed, I often don't really worry about the missing information here. I just tend to issue dates saying it's likely this sample comes from somewhere between here and somewhere here. So those dates would be actually 1377 BC to 1126 BC. So as you can imagine, in this case, you've got about 150 years or something of precision in that one date. And that was kind of where we were about, 20 or 30 years ago. That's as good as we could get. A simple calibration of an individual date or group of dates. But this process of calibration has been updated all the time. The initial blue curve was, I think there was one before 98, but certainly there was 98, 2004, 2009, 2013, and we're expecting one out now, 2020. And in Nature just the other day, they had a sort of article about this, the issuing of this new calibration curve, because it has such an important role to play now in correcting dates, calibrating dates for archaeology, but also for paleo-environmental science and all sorts of other things, geology even. So there's a picture here of tree rings. I won't today go too much into the issue of marine calibration, but that's a whole new kettle of fish, quite literally, I guess. A lot of the radiocarbon goes straight into the ocean, as I said earlier. So when you're dealing with animals or fish and mammals and things, and even plants from the sea, and you're trying to calibrate the dates on those, it's not possible to use the normal tree ring based or atmospheric calibration curve, which is shown here in green with all its structure and detail. It turns out that even though a lot of the radiocarbon goes into the ocean, it actually resides there for such a long time, especially in the deep ocean, that there's time for that carbon to decay. And so actually, on average, with the upwelling from the deep oceans, with the circulation in the ocean in general, the ocean has a lower concentration than the atmosphere. And this difference, if turned into into absolute time, would be about 400 years. So if you were to catch a fish from the ocean sort of today, and then measure its radiocarbon concentration, it would probably appear to be about 400 years too old, because it's growing up in an environment that's essentially 400 years, the equivalent of depleted in radiocarbon compared with the atmosphere. So we have the 4AM-based, basically marine curve, and also corals and things that we use for the correcting radiocarbon dates, because they already look too old. Instead of bouncing them off the atmospheric curve here, you have to continue through the atmospheric curve and bounce them off the blue marine curve here. So it actually adjusts the dates and makes them younger, because at the moment they would look too old if you use the radiocarbon atmospheric curve. So if you've got a marine sample, you have to calibrate it against the marine curve. The next big step really in radiocarbon dating was the introduction of Bayesian statistical modeling, which allowed us to get essentially decadal resolution. So Thomas Bayes was a scientist who lived in the 18th century in London, and he devised a probability theory that is really a different paradigm from what is now called classical or frequentist statistics, an entirely different way of dealing with statistics. It was all mathematically sound, and people accepted it, but it wasn't really employed for really a couple of hundred years, because the calculations you needed to do, in fact, the integrations you needed to do to make the probabilities meaningful, were too difficult to do by hand. And indeed, still now, you can't do them by hand, but we have computer technology that's able to run algorithms, sampling algorithms, that give approximations of the integrals. So from the start of the computer age, Bayesian statistical modeling has become a really big thing, not just in radiocarbon dating or in archaeology, but in in economics, in marketing, in climatology, and all sorts of fields of science, actually. And what it involves is it looks deceptively simple. It can be quite complicated, but effectively there's two main parts to it, really. One is called the they're all probabilities, but one we refer to as the likelihood. And the likelihood essentially we can regard as the radiocarbon date, that probability density function we get from the radiocarbon information, really, the data. And one multiplies that by another probability, which is called the prior probability. And this is just an assumed distribution over the years that you think that sample comes from. Now, that sounds biased, and to a degree it is. But if you express every year as equally likely over a, you know, a rationally long enough range, then it's we believe a perfectly legitimate way of analyzing the data. What sort of prior information can you employ? The thing is that you can get all of these radiocarbon measurements together, and this prior information, which we usually in the first instance regard as uniform for things we don't know the age of in the past, we give every year equal likelihood, essentially. But there are times, what the great thing about Bayesian statistical analysis is this prior function allows you to use information that you already know to be true. They are assumptions, but you know them to be true on some other grounds. For example, from archaeology. If you've got 3 samples here and they come from 3 layers in a stratigraphic sequence, and the archaeologist tells you the first one has to be older than the second one, has to be older than the third one, or indeed phase 3 has to be older than phase 2, older than phase 1, then we can bring that, express that relationship mathematically into the computer algorithm, and then we can recalculate these radiocarbon dates, and we can, knowing that they have to form this sequence, and we produce updated probabilities for those particular dates, because they have to conform to this known sequence. Now, you have to then express your results saying, well, we based our results on these assumptions, that they did actually fall into this order. And if that ordering is not correct, then your results are not correct. But by and large, if you use really robust prior information, this is a really good way of refining your radiocarbon dates. And in fact, it's not all that illogical. It actually fits perfectly well with sort of common knowledge or our common understanding of probability. Here's an example of a medieval document from England, and it's signed by these 5 characters here: Bishop Robert, Archdeacon Reginald, Precentor John, Bishop John, and Canon Richard. Now, there are historical records to show over what periods of time each of those people were in their office, had those titles. They all signed the same piece of paper. Therefore, we can deduce, really, just like reducing the, using these known date ranges, but we can deduce that this document must come from the sort of combined date of them all, because it's signed by them all. And that's the sort of thing we do in radiocarbon with Bayesian modeling. We take our probabilities and we use other information we get from completely different environments, from archaeology or from geology or whatever it might be, history even, and then we bring those into the algorithm, and then we reduce the probability ranges that way. We can do this. A lot of people don't sort of appreciate that the moment these gray distributions are created, really, they are probability densities. And it doesn't matter so much where they come from at that point. They could come from rolling a dice in a casino or some other probabilistic process. They are now subject to the laws of probability. So you can apply probabilistic paradigms on them, like the Bayesian paradigm, and use these computer algorithms to then reduce the probabilities, reduce the range of your probabilities. And increase the precision. So this is kind of where we were about 10 or 15 years ago. And here's some famous examples. The eruption of Thera, which is now back in the news for reasons that have come to play after this paper. But there was a big Bayesian model produced for that, and that was the date range produced at the time. And on the right-hand side, this was a chronology, part of a chronology built for Egypt, and this is the New Kingdom part of it, when Nefertiti, Tutankhamun was around and so on. And by using all of the relative information, all the Egyptological information that was available, including things like the ordering of the kings, which was established, has been established over hundreds of years, and even known estimates of the probable lengths of their reigns, we were able to put that into an algorithm and produce date ranges that were about 20 years for the accession dates of each of these kings, sometimes 25, sometimes 30. But you've got a lot of information, a lot of historical information in Egypt that you can use in that sort of situation. So there we were, around 2010, 2012, that sort of time period. And Bayesian modeling looked like it was the best we could ever do with radiocarbon dating. And that would bring us down into the sort of decadal range, and that would be really great. And then Japanese lady, young woman, really postdoc at the time, I believe, was making measurements on known age tree rings from Japan. And she got this data. And of course, you have to double check something like that, and you do it again. And what she noticed is that over this period, where we already had decadal blocks of data, where we already had, because we had to produce our calibration curve, so we had to measure wood going back through time, because it's so expensive to make radiocarbon dates, and because people thought the concentration of radiocarbon in the atmosphere, even though it was going to change, it wasn't going to change that much from year to year. We tended to make our calibration curve in 5-yearly or 10-yearly blocks of wood. So you got these sort of smooth averages. And you can see the smooth average on this coming slide. Sorry, the jump there was about 12 per mil, when normally people would expect the concentration of radiocarbon in the atmosphere to vary a little bit as Earth processes take hold, maybe 1 per mil, 2 per mil per year, and gradually things would fluctuate, but not jumping 12 per mil in a year. So here, the gray line in behind the colored lines represents where the calibration curve was over that time period. And it was all smooth. It did go up, and it actually went up more dramatically than anywhere else in the sort of last 5,000-10,000 years, but it didn't show a single year jump. However, Fuzumiyaki measured this wood and was confident in her results. And she said, no, it jumps up 12 per mil in 1 year. And this actually this was published in Nature in 2012, and everybody rushed out and went to their local dendrochronologist and got some wood from this time period and measured the radiocarbon concentration in the consecutive years over this particular time period, 775 of the Common Era, 775 AD. And each and every one of them showed a big jump in this year, a jump of almost exactly the same magnitude. Indeed, we measured it in the Netherlands, the white line there, a couple of years ago. And because you know these come from wood, come from tree rings that you have the age of, you already know the age of each and every one of those tree rings, you know the year in which that jump took place. Now, before I talk about why that's extraordinarily significant for dating now and for the prospect of single year dating, these events, sometimes called Miyake events after the discoverer, pose a threat to digital civilization that we live in, because the amount of radiation, it quickly became apparent that such a jump could not be created by any Earth system process. There are lots of volcanoes and oceans and things on Earth that can do things that generally deplete or decrease the concentration of radiocarbon in the atmosphere, but nothing increases suddenly the concentration of radiocarbon in the atmosphere before the nuclear age. And it, of course, happened with nuclear bomb testing in the atmosphere. But if you believe that we didn't have nuclear bombs in the 8th century AD, then the only way that the concentration of radiocarbon in the atmosphere could increase would be a big flux of particles, a big bombardment of the Earth of particles at the time. Now, if such a thing happened now, it would knock out the satellites straight away. Airlines, the avionics that run airplanes would be in danger or failure. The stock markets would probably collapse because it's all electronic as well, and essentially chaos would ensue. You can even get, when these disturbances of the atmosphere are so great, induced currents in the even metal piping, but certainly metal wires on Earth. So, and they surge into the substations and often knock them out. So if one of these events were to happen now, it would be a major deal for modern civilization. And so it's really important that we find out how often they happen, what causes them, and you know, and try and future-proof a modern civilization from these sorts of events. There's been nothing, as far as we can tell, like this in the last 500 years, even 1,000 years. But they also have a really big impact on the process of calibration. So we have this normal calibration curve here with a simple calibration that stretches out over a little bit over 150 years, this range here. And that was where we were with the simple calibration. Now we could extract that probability function and apply Bayesian statistics to it, as long as it fell into a sequence or some other temporal relationship, and try and reduce the errors down to, reduce the precision down to maybe 20 or 30 years or something. Well, very unlikely we would get that far, except if you're in a place like Egypt where you have so much information. More than likely it would be like 80 or 70 years or something. But the key thing here is that even if we were to measure that sample really a lot of times and reduce its error down to, say, plus or minus 8, you still hit that part of the calibration curve. You still have a very broad date. Now, what happens with the Miyake events is that they would appear in the record as something like this. Now, they would go the other way because the calibration curve is correcting for the increase in radiocarbon concentration. But the point really is that you have this flat edge that appears in a given year, and you know what that year is because you see that spike in the known age tree rings. And it really begins to boggle the mind when you realize that that spike in radiocarbon production was absorbed by every living thing at the time, in particular, every living plant. So in theory, all you have to do is get a bunch of tree rings from an old timber building, and if they show this spike, you know that that's the year 775. And then you just count the tree rings to the edge of the wood, to the bark edge, and you know when that tree was cut down and potentially when that building was built to the exact year. And so Lucas Barker at ETH in Switzerland decided to look at this church, which had already been dendrodated. They already had wood from the church, from beams in the church, and they knew it was from this time period. So they got samples of the wood from some of the beams, and they indeed saw the spike in some of the tree rings, counting outwards. They estimated that, I think the age of the church, I think it was built in 786 or a year like that. I presume, I'd have to look back, but I presume it was exactly the same year as what was obtained through dendrochronology. But the really exciting thing now is that that spike, and indeed those spikes, which are just coming to, will be present in every other historic building from that time period. They are also present in other archives. So on the left-hand side, Clive Oppenheimer did a project where there was an eruption from a volcano called Changbai-shan, which is on the North Korea border, went off about 1,000 years ago. And it left a lot of volcanic ash, tephra, all over the East Asian region. And so it's found in all sorts of paleo environmental archives and so forth. So it was a really a goal of a lot of chronologists to try and get the age of this eruption. Well, they found wood, trees covered in the tephra, killed by the eruption. And so what they were able to do was measure the tree rings of some of the wood, find the year 775 spike, and provide a date for that eruption to the exact year. Similarly, in the ice cores, because the isotope beryllium-10 is created in much the same way as a radiocarbon in the atmosphere through the flux of cosmic particles, the beryllium also spiked at this time. So they can get beryllium out of the ice cores. There's not really usually enough carbon to get good measurements on the carbon at this time. But what they did was they made beryllium measurements on individual layers of ice, which is quite a lot of work. And what they found was actually there was a spike, and this graph actually goes up further. They had many ice cores on the curve, and the beryllium spike was very pronounced in all of them. It turned out it was actually 7 years different. This one down here is Miyake's tree ring data. Actually, it was the spike in beryllium was 7 years different from the spike in radiocarbon in the tree rings. But they so trusted this result on the tree rings that they actually shifted all of the ice cores in time across 7 years. And Michael Sigel wrote this nice paper in Nature a few years ago and showed that by moving the ice cores by this amount, they were able to confirm various volcanic signatures, sulfurous signatures and so on, at different layers in the ice core, and they married up much better with historical records. So indeed, I think the ice core people had already been looking really for a reason to shift their ice core counting by this amount, and this gave them the scientific data by which, the means by which they could do this. So this form of getting absolute year tie points and sticking down chronologies or dating individual buildings and so on to the year is, of course, very dependent on finding more of these events. So the race was on really to discover them, and Fuzumiyake published one in 775 and then another one in 993 a couple of years later in another Nature journal. We think that the one in 660 BC, it may not be exactly quite the same thing, but it looks very similar to the other two. It's definitely a rise. Whether it comes in 1 year or not, it's a bit debatable, but certainly there's a distinct signal in 660 BC. I've heard people talk at conferences about one in around 1220, 1218 of the Common Era, but that's not yet been published. And there was one published a couple of years ago, quite some time back, sort of Neolithic age, but it has since been challenged just this year by people measuring that wood from other locations. We had a look at this ourselves. I was not doing it very scientifically at the start, and I was looking at 540 CE. There was definitely a decrease in radiocarbon age at that time. So I got individual years of wood and we measured them. And there's clearly a deviation, and it's a 5 per mil deviation, which is quite a lot. But 5 per mil in 4 years, 1 per mil per year, that's not really the same as a 12 per mil jump in a single year. So this is probably not a sort of feature that we can use for dating. It's certainly not the same sort of Miyake event material. And I employed a machine learning person, expert, to go through all the decadal data that's knitted together to make the calibration curve, all the tree ring data from all the different archives that's used to put together to make the calibration curve, to try and identify with his methods where he thought there might be spikes. And we published this last year. And of course, now requires us to go and get known age wood from these periods and measure them and see if there is spikes there, or if there are spikes there or not. So that was a part of this project we had called Echoes, and it was done by actually Andreas, who was a postdoc on the project. We have our Twitter and we have a website and so on. And it's sponsored by the European Research Council. The ultimate goal of echoes, though, is to apply it to archaeological contexts. And we've had our first major success just recently. And unfortunately, if I was giving this talk next week, I could talk about this paper in more detail, but it's coming out next week. And it's an extraordinary site in Russia, very mysterious site in Siberia on an island in a lake. And its use or its origin was disputed for a long time. And we were able to talk to the excavators there and get some beams from the very basal layers of the foundations of the structure and measure the radiocarbon concentration of them. And indeed, we found the year 775 spike in them. So this location called Pobajin, we were able to date to the year. Other things we hope to do in time, archaeologically speaking, are use the difference as well between Miyake events to test durations at particular locations where you might have timber buildings from one time period to another. We know that in the year 993, there's a jump. It's not as big as 997, but it's clearly there. So you know this difference is exactly 219 years. These sorts of exact year estimates is where this research is now going to go. And ultimately, the holy grail that I'm working on as part of this ECHOES project is to try to extend the exact year timescale back in time. A lot of people don't realize that actually annual history runs out in the first millennium BC. There are Chinese records, Sima Qian and the great historians, who actually wrote these records many centuries later, but they have yearly records that go back as far as sort of 841 BC. Before that, it becomes a little bit ambiguous what the exact years are. In the West, there was an eclipse, I think, in 763 that was recorded in Mesopotamia. And after that, we can situate all historical events in exact calendrical time. In Egypt and in Mesopotamia and in China, we have records that go back much further, but there are gaps in them. And we don't know exactly, sometimes these very long conjoint sequences, like for example, in Egypt, you have the Old Kingdom, the Middle Kingdom, and the New Kingdom. They all hang together, but they're floating in time. We don't know exactly, especially when we go further back in time, where exactly they are. So the really great thing to be able to do with a Miyake event, and nobody's going to do this yet, we'll be able to find one in an archaeological context that's directly linked to the Egyptian chronology, the Mesopotamian chronology, or the Chinese chronology, so that you can situate some of these floating sequences exactly in time, and then we'll know precisely what years it was in which all of these important events in early civilization took place, and indeed compare those events with other archives like environmental archives that are dated annually, or at least on the absolute timescale. And it really will unpick a lot of the analysis of early civilization. Here is my final slide about how hopefully with this sort of new dimension to radiocarbon dating, we will be able to pin these events together, and so that the West and the East and any comparisons can be made are actually made on absolute years by placing these important historical events exactly in time. Then we can really trace the origins and the propagation of technology and other ideas. And that's what I've got to say today. Thank you very much.
All right. Thank you, Mike. We do have two questions in the moments we have remaining. From Richard Wade. So, if Miyake events represent an increase in atmospheric radiocarbon, how does that square with heliospheric activity, which is supposed to suppress spallation?
Well, this is really a brilliant question, I have to say. This really is a very good question. And I didn't go into any of that today. And indeed, I could have done. I could have done a whole talk on these events and what causes them, or what we think causes them. So there is this strange anti-correlation between solar activity and radiocarbon production. When the sun is very active, production is very low for the reasons I talked about. And indeed, we also know that the sun does not produce particles at the sort of energy levels that could break up nuclei and produce radiocarbon in the upper atmosphere. So then, if the sun is responsible for these events, it has to have given off particles at extraordinary energy, and somehow they have to have made their way into the perhaps spiraled in through the geomagnetic field, in through the polar regions, and somehow or other smashed up nuclei. That is one of the big outstanding questions in this area of research. A lot of people say that the question is no longer outstanding, that indeed it is the sun. And the reason for that is because there are apparently so many of them, and no other sort of galactic event could have, well, I wrote a paper about it potentially being supernovae, which do occur quite regularly, actually about once a century in our galaxy. We measured over the supernovas, and we didn't really get any correlation with this sort of, with the known supernovas from the past, and we didn't get any correlation. So there is also some isotopic evidence from the ice cores and so on. And there's a lot of sort of anecdotal evidence that it is likely to be the sun. We really need to find concrete proof of that, or that each and every one of these events is caused by the sun. And how that circle is squared is difficult to know. The current thinking is that it's something called solar superflares. Now, on some other stars in the galaxy, it can be seen that stars similar to the sun can produce flares up to 10,000 times the size of any flare we've ever witnessed on the sun. So it could be that for some freak reason that requires a lot of physics to understand, the sun is occasionally capable of shooting off enormous flares that do actually cause these spikes to occur.
I think maybe this would be a short yes or no type question. This is, does the Carrington event in the mid-1800s manifest in a Miyake event, or as we would see it in the curve?
That's another brilliant question, and we measured, and in some other slides that I show, I tend to show the radiocarbon record over the Carrington flare, which was really the largest solar storm in the last few hundred years, happened in 1859, and we see nothing. We see absolutely no increase in radiocarbon whatsoever over the Carrington flare. Some people think that doesn't matter. They think that these other events in 775, 994, and perhaps the earlier ones in time were just orders of magnitude greater again than the Carrington flare. That in order for, because there is a threshold, in order to smash the nuclei in the upper atmosphere, you have to get up into the mega electron volt sort of energy ranges. And it could be that the sun let out an enormous flare, like the Carrington flare, and it's still the spectrum of particles that came to Earth, the energy spectrum wasn't great enough to create a spike. But that's another reason why it leaves a little mystery to the problem, because if the biggest solar storm we've ever seen creates nothing, it's still quite interesting to that people fully ascribe them to the sun.
Okay, now this question comes from Jose Capriles, who's on our faculty here. And it's about something I wanted to ask about anyway, with the new curve hopefully coming. How are these events incorporated in the new calibration curves, and how will they affect calibration? So kind of adding to that, Mike, do you know like where we stand with that? And I know Stuart Manning has talked quite a bit about going back to the single year, or maybe the actual error models for like in Cal 98 being more effective for wiggle matching and this kind of thing. You know,
Um,
we'll still be including the 5 and 10-year chunks as we keep adding single year to the curves. But what is your take on that?
I have to be obviously very careful what I say here because it's one, I'm not on the panel, and I'm not involved really in the discussion around how they knit together those data points. And I have been to conferences where this is talked about, so I think that I can say some things. From what I understand, the calibration curve will be single year over the last few thousand years. But it's not going to be, I don't think, of the nature of the 98 one. I think it's still going to be knitted together and that kind of smoothed in a certain way. So I don't think, actually, unfortunately, that like the 775 event will show as the really vertical spike that it is. You know, that you see in Miyake's data. I think by the time you get all the data mixed in and you draw even in a single year sort of average through it, I can't speak because I actually haven't seen like the final curve or anything like that. But I think we might unfortunately be missing some of this really important substructure, some of this really important information by I mean it's I guess a rock and a hard place because they need to incorporate all of this data and they want to make it, I guess, usable as widely as possible. You know, there are potentially small offsets, really small, but still offsets from one place to another place, maybe even at different altitudes and things like that. So they have to produce this consensus curve. And indeed, it all, in the end, has to be a kind of an average thing. But I fear that it still, unfortunately, won't have the really nice detail that we need. It would be a big improvement, I think, on where we are. But in truth, I don't know, and I'll have to wait to see what it looks like when they finally release it as well.
Yeah, no, I hear you. It is, you know, it's almost as we're getting in, you know, with the kind of regional corrections that are possible, then, you know, it sort of kind of reminds me of like, you know, the Fairbanks, the 04 InCal curve and the debates about that and who owns the past and, you know.
I agree completely. And I think that we're at a funny stage now where I think, and there are various people on the committee who could do this, I think, and hopefully they will, we should progress towards a sort of a spline, a central curve, and then a function that relates to your location and maybe even the type of wood or something that gives you an opportunity to correct your results based on your exact location, kind of like we do, but much better than the marine calibration curve, where you have the local delta R's. We have something more sophisticated because people are trying to push now towards annual data, and they are trying to push towards really single year dates for their structures and so on. You know, we do have the capacity to do that in certain circumstances. But for example, on our site in Siberia there that I talked about, we really constructed our own curve over that period. We had to get, you know, known age records over those years and measure them and compare our data with those. And with various versions, we made our own sort of calibration curves, which is what they did too in the 80s and 90s before InCal came around. People were making their own curves and calibrating against their own records. We try to get rid of that process by having a collective curve, but yeah, you're always going to lose some detail when you do that, I think.
Yeah. Okay, we are running a little bit over, but another, let's see, quick question or whatever. These are all from the same guy, Richard Wade, asking the excellent questions. So if solar super flares, is there any written or pictorial record, say with these, and how would a human experience this? Extinctions?
I think I should quite like to meet this guy. These are really excellent questions. And I have done some work on this as well. So as this person probably knows, during the Carrington flare, this massive solar storm created the aurora, enriched the aurora, the northern lights which I don't suppose you can see where you are, but if you go a little bit further up in Canada and up here in if you go up into Scandinavia from here, you can see them. That's the sort of electronic activity of oxygen molecules and so on in the atmosphere, stirred up by these particles coming from the sun. Now, during the Carrington flare, the aurora could be seen, there's records of it, from Hawaii and from the Caribbean. So presumably over North America and Northern Europe, the sky was just blue and green and completely for perhaps many days. It would have been spectacular. So if that was the Carrington flare, what did that mean for the year 775? If we believe it to be the sun, then surely something extraordinary happened in the sky. And I have to say, again, the stories fall short a little bit here. People have looked into the historical aurorae. The Chinese have really great records at this time. They really kept excellent records of the night sky. Korea as well, Japan. But even in Western Europe, there are some good historical records. And, you know, there doesn't seem to be really, I think, a very compelling, sort of convincing historical description of the sky, you know, being colored for a long period of time or anything like that. There is an entry in the Anglo-Saxon Chronicle from exactly that year that says, in this year, the sky was filled with a red crucifix, which you can, I guess, take what you like. I mean, maybe it's relating to this event, maybe it's not. But yeah, it's something that, it's another avenue. Indeed, I thought in the beginning it might be an avenue for finding these events. Go to the historical records and see where the sky, description of the sky was sort of unusual, and maybe measure over those periods first. Yeah, I don't, in answer to your question, how would people experience them? Well, the actual increase in radiocarbon was quite small compared with, say, like the bomb curve. The bomb curve went up 1,000 per mil, basically doubled, where we're talking up by 12 per mil, you know, so 15 per mil or some number like that, but, you know, orders of magnitude lower than the increase due to the nuclear bomb tests. So indeed, it's not like enough to cause any sort of major biological effects. But I think too that someone should be able to find a historical record that describes something that can only be attributed to these events in these years. You read various papers and you find some people claim that they are doing that, but I haven't yet really seen something that I think is really, really compelling.
Yeah, I think we'll leave it there. Thank you, Mike, especially for entertaining these questions. You know, it's really getting into the nitty gritty with how radiocarbon works, you know, and as I've always thought, you know, if you get tired of thinking about the archaeology or some other thing, you know, you can get into the physics, the astrophysics, the biology, plant physiology. And it's just a really great example of how radiocarbon touches on so much.
Shall I stop sharing if you want to?
And yeah, and I will pause. So thank you all very much.